Okay, so in this video, we want to consider the topic of extrema of a function y equals f of x. Extrema is the plural of the word extreme, therefore extreme values. So we're looking at the global maximum and global minimum of a function. And this will be helpful when we consider problems of optimization. And those will be in our next videos. But for now, there are two questions here. The first question is, under what conditions do we know for sure that the function f of x will attain a maximum and a minimum value? And the second question is, if we are under these conditions, so we know that f of x will attain a maximum and a minimum value, how do we look for maximum and minimum values? So where do we find those points? So let's just look at first an existence theorem. This is called the extreme value theorem. So the result is actually really nice because there are only two conditions that the function and the interval must satisfy. So let f of x be our function, be continuous, on a closed and bounded interval. Say the interval from a to b, where a and b are fixed real numbers, where obviously a is less than b. So we have just two conditions. F of x is continuous on a closed and bounded interval from a to b. So bounded means that the interval is finite, so both a and b here are fixed real numbers. And closed means that we do include the end points in our interval. So our interval goes from a to b, including the left endpoint a and the right endpoint b. So there are only two assumptions here. The interval is closed and bounded, and f of x is continuous on this interval. Then what the extreme value theorem says is the function f will attain a maximum and a minimum value on this interval. So we'll attain both a maximum and a minimum value on the interval AB. So imagine that we are restricting our graph of f of x to the interval from a to b, and if f of x is continuous, then it will attain a maximum and a minimum value on the interval a to b. We usually, this is now the result, so as long as we have a closed and bounded interval and a continuous function, the extreme value theorem guarantees that the function will attain a maximum and a minimum value inside of this interval. Now, how do we denote these points? And let's look at a few definitions. So, the minimum value is attained at a given value of x inside this interval, and we usually let x sub m denote the point at which f attains a minimum value. So we usually let x subscript lowercase m to be the global or absolute minimum of the function f on this interval. So we let xm be equal to the global. And a synonym of global is absolute. Minimum of f of x on, because we are restricted the function on a to b, so on the interval from a to b. Well, what does that mean? If xm is a global absolute minimum of f of x on ab, It means that the function f attains its smallest value at this point. So, if you take the value of f at this point, because this is a minimum value, a minimum point, sorry, of the function, then the value of the function at this point must be less than or equal to any other value of the function, x, so for all other points x inside of the interval. So you see, simply put, xm is a global, or you can say absolute minimum of the function on AB if any value of the function at any point inside the interval f of x for any x in the interval is at least as big as the value of f at this point. And we say that f of xm is the minimum value of f of x. So the global absolute minimum of the function is a value of x inside the interval where the function f attains its minimum value. So f of xm is less than or equal to f of x for any other value x in the interval. And of course we will use x subscript uppercase m for the absolute global maximum. So we let x subscript uppercase m now for the maximum. This is the global slash absolute, they are synonyms, maximum of the function f of x on the interval from a to b. So what does that mean? Well, the value of the function at its global absolute maximum must be greater than or equal to any other value of the function for any other point inside the interval. And of course, this is the largest value of f attained inside this interval, so we call this the maximum value of f of x on AB. Okay, so we have here our theorem and our notation. X subscript lowercase m is the absolute or global minimum of the function on the interval a to b. Therefore, the point for which the function f attains its smallest possible value. X subscript uppercase m denotes the global or absolute maximum of the function on the interval. So it is the value of x where the function attains its largest value on the interval. Therefore, the maximum value of f and the minimum value of f. Now, to prove this result, to prove the extreme value theorem, that for any function that is continuous on a closed and bounded interval, that a function of this type will attain a maximum and a minimum value inside this interval, this is a rather non-trivial result to prove. But it's at least try to get a feeling for why the result makes sense intuitively. And the argument we're going to use is slightly flawed, but at this level we'll just go with this really heuristic argument. Remember that continuity means that there is no break in the function. So at any given point, the value of the function exists, and the limit of the function as we approach this point equals the value of the function at this point. So continuity means that there is no break in the function. And this is where we use a heuristic, and this is again, theoretically it is slightly flawed, but for us we'll be happy with that. Since there is no break in the function, imagine that you would sketch the graph of the function y equals f of x. If there is no break in the function, you can imagine sketching the graph without ever lifting your pen. If you lift your pen at some point, there will be a break in the function, Because of continuity, there is no break in the function. So imagine sketching the graph of y equals f of x on the interval ab without ever lifting your pen. So suppose we have the following picture. Your y and your x-axis. Just for argument's sake, we will assume that the values of a and b are positive. So suppose this is a, and suppose this is b. And now suppose we start our function y equals f of x, say, here with, let's go with the positive value. And now imagine sketching the graph of a function from a to b, and because it is continuous, you cannot lift your pen, because if you lift your pen going from a to b, there would be a break in the function, and we, by assumption, assume that f is continuous, therefore there are no breaks in the function. And you can imagine drawing any possible graph from a to b without ever lifting your pen. Suppose we go like this, then the function comes back up, and we end here. Then you can see that indeed the function attains a maximum and a minimum value, right? This is the minimum value attained by the function. So this is the point that we call the global or absolute minimum. So x subscript lowercase m. So xm is our absolute global minimum, and the minimum value attained is f of that point. So f of x subscript lowercase m. So here's our absolute minimum value. I'm sorry, our absolute minimum of the function, and this is the minimum value attained by the function. And if you notice, here b would be the absolute maximum. So x subscript uppercase m. At this point, the function attains its largest value, and the maximum value is, of course, the value of the function at its absolute maximum, or its global minimum, f of x lower subscript uppercase m. And you can imagine drawing any possible function you can imagine from a to b without lifting your pen, and you will always have a point where the function attains its minimum value, and this is called the absolute minimum, and another value of x where the function attains its maximum value, and this is called the global or absolute maximum of the function. And this is how you should think of the extreme value theorem intuitively. If you sketch a graph of the function f of x on the interval ab, because f of x is continuous, then you have to sketch the graph of the function without ever lifting your pen, and because of that you will reach a minimum value and you will reach a maximum value. So that's the existence part. As long as you have a closed and bounded interval from a to b, and you include both endpoints, you are guaranteed that the function will attain a minimum value and will attain a maximum value inside of the interval. The question is now, and this will be key to our problems of optimization, if you want to maximize a function, you look for its maximum value. If you want to minimize a function, you look for its minimum value. And this is the heart of optimization. You will either minimize or maximize a target function. The question is, where should we look for a maximum value or a minimum value? So this is the second part of our discussion. If we do have a function that is continuous on a closed and bounded interval, we are guaranteed the existence of a global minimum and a global maximum. The only question is, where do we look for the global minimum and the global maximum? Let's look at a few basic examples, see if we can notice something interesting, and then we'll prove that what we guess as a result will actually be true. Let's consider a few basic continuous functions on a closed and bounded interval and ask ourselves, where does the minimum value occur and where does the maximum value occur? And hopefully we'll notice something interesting. So let's start with something really simple. Let's consider the function y equals 2x, let's go with y equals 3x on the interval from 0 to 2. So this is our function, y equals f of x equals 3x. And this is just a line, so we know it's continuous. And our interval is from 0 to 2. So we have a closed and bounded interval, a continuous function. By the extreme value theorem, we know that this function will attain a maximum and a minimum value on the interval. Well, if you sketch y equals 3x, 3 times 0 is 0, 3 times 2 is 6. And so the function will look something like this. Obviously, from the picture, my axes are not up to the same scale. Doesn't matter. And you can clearly see that xm, the absolute minimum, is equal to 0. At this point, the function attains its minimum value. So this is our absolute minimum. And the minimum value of the function is, of course, f of this point, which is f of 0, which is simply 0. So x equals 0 is our absolute minimum, and the minimum value attained by the function is 0. And where does the absolute maximum occur? Obviously at 2. So x equals 2 is our absolute maximum, our global maximum, and the maximum value attained by the function is f of 2, which is obviously equal to 6. So you see x equals 2 is our global maximum, and at this point the value attains its maximum value of 6. Now what's interesting here? The absolute minimum was the left-hand point of our interval, and the absolute maximum was the right-hand point of our interval. So it is obvious from this problem that if you ever want to maximize or minimize a function that is continuous on a closed and bounded interval, you have to consider the endpoints, because a maximum can occur at an endpoint. As you can see, the minimum occurred at the left-hand point, and the maximum value occurs at a right-hand point. So if you ever want to maximize or minimize a function that is continuous on a closed and bounded interval, one must consider the endpoints. So this is our first observation. We have to consider endpoints as possible absolute minimum or absolute maximum. So we must consider the endpoints of the interval. As this example shows, our function attained its minimum value at the left-hand point and attained its maximum value at the right-hand point. So whenever you want to maximize or minimize a function that is continuous on a closed and bounded interval, we always have to consider the endpoints a, b of our interval. There are always possible absolute max or absolute min. Are there other points aside from the endpoints where max and min could occur? If you go back to our previous picture, the answer is obviously yes, right? Clearly here with this graph, the maximum occurred at a right-hand point, nothing new, but the minimum here occurred at this point. Let's look at a few examples where this could be the case and ask ourselves, what is special about this point? So let's look at a second example. Let's now consider the function y equals x squared on the interval from negative 2 to 2. Well, let's go from negative 3 to 3, say. So our function is y equals x squared, which we know is continuous as it is a single polynomial, on, this is our f of x, on the interval, say, from negative 3 to 3. So suppose this is negative 3, And clearly again the picture is not up to scale, and this is positive 3. And let's ask, well, where does the function x squared attains its maximum value, and where does it attain its minimum value? Let's look at the maximum value. And one thing that is interesting here is we'll see that the maximum value is not, the maximum value and the absolute maximum is not unique. At positive 3 squared is 9. And at negative 3 squared is also 9. So here, clearly, y equals x squared on the interval from negative 3 to 3 attains its maximum value of 9 at two distinct points. So our absolute maximum is not unique. It is negative 3 is valid, but positive 3 is also valid. So both negative 3 and positive 3 are absolute maximums of our functions, because at those 2 points, clearly the function attains its maximum value of 9. So you can see that an absolute maximum may not be unique. There may be several absolute maximums, but there is a unique absolute maximum value, which is 9. So as before, our absolute maximum, which happens at 2 points, is, in both cases, an endpoint of the interval. So we already knew that we had to consider endpoints of an interval. Nothing new here. What is interesting now is the location of the absolute minimum, which clearly is at x equals 0. So our absolute minimum value will be f of xm, right? Our absolute minimum is 0. And our absolute minimum value is f of 0, which is 0. And now if you notice, the function x squared attained its minimum value of 0 at the point x equals 0. So x equals 0 is our absolute minimum, but it is not an endpoint of our interval. It is not negative 3 or positive 3. So it is possible for a function to attain a maximum or minimum value at the point other than one of the two endpoints. What is special here about our absolute minimum? Well, let's look at the derivative of our function. So f prime of x is simply 2x. And if you notice, the only critical point of our function is where the derivative is 0. So this is 0 if and only if x is equal to 0. So you see that our function y equals x squared between negative 3 and 3 has a unique critical point where the derivative is equal to 0, and that critical point is 0. And you see that in this example, the absolute minimum of x squared happens to occur at a critical point. So obviously, critical points are points that must be considered, because as we can see in this example, the function x squared does attain its minimum value at x equals 0, which is a critical point of the function. So we also have to consider critical points inside, of course, the interval. And notice here that the critical point was of the type, the derivative being 0. So it was a point where the curve was flat. So far we have seen that a maximum value and or a minimum value can occur at one of the two endpoints of the interval, or at a critical point inside of the interval. So whenever we look for maximum and minimum values of a function that is continuous on a closed and bounded interval, we have to consider the endpoints, so the value of the function at the endpoints, and the values of the function at the critical points inside of the interval. But the critical point we had here was of the first type, where the derivative was equal to 0. so the curve was flat. Let's consider one more example where the minimum value will also occur at a critical point, but now of the second type, where the derivative is actually undefined. And we'll consider, instead of x squared, simply the absolute value of x. And we'll go on the interval from, say, -2 to 2. So our function, y, equals f of x. We will take it to be the absolute value of x. As we can see, we are gluing the two lines y equals x, y equals -x to form the absolute value function. And because they meet at 0 at the same point, the function is obviously continuous. And we consider the function on the interval -2 to 2. And now, as before, the maximum value occurs at two different points, at -2 and at 2. Absolute value of 2 is 2. Absolute value of -2 is also 2. So our absolute maximum, our global maximum, occurs at two values, at -2 and 2. And the maximum value of the function attained is 2. And there is nothing new here because the absolute maximum occurred at both endpoints. And we already knew that we had to consider the endpoints. What about our absolute minimum? Once again, as in the case of x squared, our absolute minimum occurs at x equals 0. And the minimum value attained by the function at that point is the absolute value of 0, which we know is simply 0. The question is, what is interesting about this point? Well, let's see. X equals 0 is not the left-hand point nor the right-hand point of our interval. It's not an endpoint, but what is special about this point? Let's look at the derivative on the left of 0 and the derivative on the right of 0. We know that the line here is y equals x, and the line here is y equals -x. Therefore, on the right of 0, the derivative is equal to 1. So f prime of x is equal to 1 for positive values of x. So we have a slope of 1 always. On the left now, the function is -x, therefore the derivative is -1. For -x values. And you see that this causes a bit of a problem. The derivative to the right of 0 is always equal to 1. So f prime of x is equal to 1 for any positive value of x. But f prime of x, the derivative, is -1 for any negative values of x. And one might ask, well, what is therefore the derivative at 0? So what happens to the slope of the function as we approach 0 from the right? The slope is always 1. So as we approach x equals 0, the derivative is always 1. So from the right, it approaches 1. So 1 is a possible value for the slope of the function at 0. But the problem is, if we approach 0 from the left, the slope is always -1. Therefore, the derivative of 0 should also be -1. Well, how can it be simultaneously 1 and -1? The answer is it's not possible. So the derivative of our function at 0 is undefined. It does not exist. And what's interesting is, therefore, that x equals 0 is a critical point of the second type, right? A value of x is a critical point of the function if it is a value where the derivative is equal to 0, or if it is a value of x where the derivative is undefined. And so you see that here, our global minimum, x equals 0, is a point where the derivative does not exist. So when we said that we have to consider critical points inside of the interval, we mean critical points of any type. So a point where the derivative is 0, or a point where the derivative is undefined. And so you see right now, we have three examples. And we said if we have a function that is continuous on a closed and bounded interval, a maximum value and minimum value will occur at either an endpoint of the interval, at a critical point inside the interval where the derivative is 0, or at a critical point inside the interval where the derivative is undefined. And you may ask, what if we go through, say, 10 other examples or 100 other examples? Will we ever notice something different? And the answer is actually no. You can go through 100 examples of a continuous function on a closed and bounded interval, and you will always notice that a maximum or a minimum value has to occur at either an endpoint of the interval or at a critical point inside the interval, therefore a point where the derivative is 0 or undefined. So let's prove now that this result is actually true. And the proof is surprisingly straightforward. And this will conclude our discussion of theoretical optimization. So here's our theorem. Again, we have the same assumptions as the extreme value theorem. We assume that we have a continuous function on a closed and bounded interval. So let our function f of x be continuous on the closed and bounded interval ab. So a and b are fixed real numbers, and our interval includes both endpoints, a and b. This is our assumption. And again, by the extreme value theorem, this is a result of existence. It says that the function f will attain its maximum and minimum value somewhere inside the interval. But where's that somewhere? That's not very useful. Well, now we know where that somewhere is. So then, our minimum value, our minimum point, so the absolute minimum or a global minimum, has to equal either the left-hand point or the right-hand point, or it has to be a value where f prime at this point is equal to 0, or a value where f prime at this point is undefined. And that's what we have just observed with our previous three examples. The absolute minimum occurred at either the left-hand point, the right-hand point of the interval, or was a critical point of the function where the derivative was 0, or a critical point where the derivative was undefined. And the same is true for the absolute maximum. The absolute maximum must be the left-hand point of the interval, the right-hand point of the interval, or must be a critical point of the first type where the derivative is 0, or a critical point of the second type where the derivative is undefined. And so this is great because it tells us exactly where to look for absolute maximum and minimum of a function. We only have to look at the endpoints of our interval and at critical points. Those are the only points where a function can attain its minimum and maximum value. So we can write this in words. So in words, f of x can only, as long as it is continuous, can only attain its maximum slash minimum. The result is true for a maximum or minimum value. So f of x can only attain its maximum slash minimum value at one of the endpoints of the interval, so at an endpoint of AB, or the only other option is a critical point inside of AB. And that's it. So if we combine this result with the extreme value theorem, we have a really powerful result. If you ever want to maximize or minimize a function that is continuous over a closed and bounded interval, the extreme value theorem says that the maximum value does exist and the minimum value does exist. But the question is, where do we look for the max and min of a function? And this result is it's quite simple. The function can only attain its maximum and or minimum value at an endpoint of the interval, so either a or b, or at a critical point in the interval. So a value of x inside of ab, where the derivative is 0 or undefined. Let's prove our result. The proof is surprisingly simple, and we'll prove it for the case of a maximum value, and I will let you conclude the proof for the minimum value, and you will see it's a copy-paste of the argument for a maximum value. So let's look at the possibilities. Either our maximum or absolute maximum occurs at an endpoint of the interval or is inside the interval. So either xm is a, b, or xm lies inside of the open interval ab. Those are the only two possibilities, right? A point in AB is either the left-hand point, the right-hand point, or somewhere strictly in between AB. Well, if xm is A or B, we're done, because the result says that if you look for a maximum value of the function, it has to be a endpoint of the interval, so either A or B, or a critical point. So if right away xm is A or B, we are done. So if our absolute max is A or B, the result is true, so we're done. So we can assume that xm is somewhere strictly in between A and B. If you prefer to this notation, you can write this, that xm is strictly lying inside of the interval. Well, once again, in this case, there are only two options. Either the derivative of the function exists at this point or not, right? Those are the only two options. So there is case 1. The derivative of the function at the absolute maximum exists. Or there is case 2. The derivative at the absolute maximum does not exist, so is undefined. And now think of it. At this point, there are only two options, right? We said if our absolute maximum is the left or the right-hand point of the interval, we're done. This is part of our conclusion, because we said that a max can be the left or the right-hand point, so we're done. So if it's an interior point of the interval, either at this point the derivative will exist, or the derivative will not exist, therefore is undefined. So if we are in case 2, we're done, because if we have a point where the derivative is undefined, this value is a critical point. So if we are in case 2, we're done. So if the derivative at our absolute maximum is undefined. By definition, xm is a critical point, which is part of our conclusion. So the only case left over is, what if the absolute value is an interior point of the interval and the derivative at this point does exist? Well, let's look at our conclusion. The result says that the function can only attain its maximum or minimum value at an endpoint of the interval, so either a or b, or at a critical point. Well, clearly we are in this case, so xm is not an endpoint of our interval. The only other option in our statement is that the absolute maximum will be a critical point. Well, if the derivative at xm exists, and xm is a critical point, well, the derivative at xm must be equal to 0. And if we can show that, then we're done. If the derivative at the absolute maximum is 0, xm is a critical point, and we have proved the result. That's what we have to show now. So we are in case 1, assuming that the derivative at the interior point xm does exist, and we must show that the derivative at the absolute maximum, since it does exist, and the conclusion only allows for endpoints or critical points, and because xm is neither the left nor the right endpoint, the conclusion only allows xm to be a critical point, and because the derivative exists, it must be a critical point where the derivative is equal to 0. So if we show this, then we're done. Well, how do we show this? Well, we have to go back to the definition of the derivative. You'll see the proof is surprisingly easy. First, by assumption, if you remember, xm is our absolute maximum, our global maximum. So we know that at this point, xm, the function attains its maximum value. So the value of the function at this point is at least as big as the value of the function at any other point inside the interval. So this is true, because xm is the absolute maximum, so at this point the function attains its largest possible value inside of the interval. Okay, so now where do we go from here? Imagine the following picture. This is your x-axis. This is the left endpoint A, the right endpoint B, and this is now your absolute maximum, some value of x inside of AB. For any x other than xm, the value will be less than f of that point, or equal to. Let's look now at the derivative of the function f at this point by the definition. And all we need to show is that the derivative at xm is 0. So you say, okay, what is the derivative of the function at xm? By definition, we are letting h approach 0. And we take f of the value xm plus h minus f of xm divided by h. And that's the derivative of the function at xm by the definition. Well, because this limit exists, we can let h approach 0 from the left or from the right. In either case, the value will be the derivative of our function. So let's do that. The derivative, because when we say that h approaches 0, it can approach 0 from the left or from the right, but either case, because the limit exists, the limit from the left and from the right must be equal. So let's see now. We are approaching 0 from the left, and we consider f of xm plus h minus f of xm over h. And let's see what's interesting here. Look at your denominator. Because h approaches 0 from the left, h is negative, So our denominator is strictly less than 0. Look now at your numerator. F of xm is the largest possible value attained by the function f. F at any other point is less than or equal to xm. Well, look at this point, it is xm. Because h approaches 0 from the left, h is negative, so we add to xm a small negative number, so we get roughly this point. And this is now a point other than xm, and f at that point is less than or equal to f of xm, because the function attains its maximum value here. So this value is less than this value, or equal to. So because this is the greatest value of the function attained by the function, this is at most 0. Because f of xm is bigger than or equal to any other value of f, so some value of f minus the greatest value of f can only be in the best case 0 or less than 0. But think of it now. You take the limit of this fraction, the numerator is always less than or equal to 0, and h is always strictly less than 0. So something at most 0 over something negative can only be either positive or 0. So the derivative must be greater than or equal to 0. Think of it this way. Either the top is 0, in which case the derivative is 0, or the top is strictly negative, but then you have a negative over a negative, that is a positive. So from the left we get that the derivative of the function at its absolute maximum has to be at least as big as 0. Let's look now at the derivative from the as the limit from the right. So the derivative of our function at its absolute maximum will be the limit as h goes to 0 from the right. It's still the same expression. So it's f of xm plus h minus f of xm over h. And let's see what's interesting here. H approaches 0 from the right, so h is slightly bigger than 0. So our denominator is positive. The numerator is the same as before, right? We add to xm a small positive number. So now we have the value of the function at some other point inside the interval. So we know that this value is at most this one, because f of xm is the largest possible value attained by f. So the result of our subtraction, because this is at least as big as this, is again at most 0. So now think of the two options here. If the numerator is equal to 0, you have 0 over a positive number, so the limit is 0. If the top is strictly less than 0, you have a negative over a positive, so it's negative. So either the ratio is negative or is equal to 0. So in the best case it will be 0, but it can never be greater than 0. And why is this interesting? Well, look at this. The derivative of f at its absolute maximum is at least as big as 0. From the limit from the left, so the derivative at xm is at least as big as 0. But from the limit from the right, the derivative at xm is less than or equal to 0. And now look at that. How can you have a number that is bigger than or equal to 0 and simultaneously less than or equal to 0? There is only one option. This number must be equal to 0. And so you see that the absolute maximum, of our function is a critical point. It is a value of x where the derivative is equal to 0. So xm is a critical point. And this completes our proof. Let's just go back to the statement. The statement said that if you have a continuous function on a closed and bounded interval, we know it will attain its maximum and minimum value, and the result said that a maximum can only occur at either a or b, the left endpoint of the interval, or it must be a critical point inside the interval. So we said, well, any value that is an absolute maximum will be inside the interval, so it's either a or b, or strictly in between. If our absolute max is a or b, this is part of our conclusion, so it's good. So if it's not a or b, then our point is strictly inside of ab. And there are two cases at this point. Either the derivative at this point is undefined, in which case xm is a critical point, which is part of our conclusion, or the derivative is defined, and then you say, well, okay, the derivative could be 5, could be 7, we don't know, but we need to show that xm is a critical point. And so we looked at the derivative of our function at xm, by the definition, from the left we get that the derivative is at least 0, from the right we get that the derivative is at most 0, therefore it has to be 0, therefore absolute maximum is indeed a critical point. And this completes the proof. So when you look for a maximum or a minimum value of the function and you say, well, where could it occur inside the interval? The answer is remarkably simple. It will either occur at the left-hand point of the interval, or at the right-hand point, or at some critical point inside the interval. So you only ever have to watch for or verify the value of the function at the two endpoints of your interval and at every critical point inside the interval. Let me give you, this was the rigorous proof. This is a really solid proof that the result is true. Let me give you a really simple heuristic argument as to why you can prove this result in a sense heuristically without doing any kind of work. Think back to the derivative as the slope of your function, the rate of change of your function. So whenever the derivative is positive, the function is increasing. Whenever the derivative is negative, the function is decreasing. So imagine that you have the following graph of the function. So you have the function y equals f of x. And suppose you have this point here, say x0. Suppose that at this point, the derivative of the function, say, is positive. Well, the derivative, as we've just said, is the rate of change of the function, or the slope of the tangent line. If you have a positive rate of change, the function is increasing at that point, or think of it as the slope of the tangent line is positive, so the tangent line is increasing, therefore the function must be increasing as well. Suppose the value at x0 is positive, just for argument's sake, and we know that at this point the function is increasing. So it may be concave down or concave up increasing. Assume it's concave down increasing. Well, clearly x0 cannot be an absolute minimum, because if you go to the left of x0, you can see that f attains an even smaller value. And clearly x0 is not an absolute maximum, because you can go to the right of x0 and clearly f will attain an even bigger value. And you get the same argument if the curve would be concave up. So it's obvious that if the derivative at this point is positive, the curve being increasing, x0 cannot be a minimum value nor a maximum. What if the derivative was negative? So if prime at x0 is less than 0. Well, draw a similar picture. Suppose this is the value of the function at x0. Again, the derivative being negative, the curve will be decreasing. Well, it could be decreasing concave up, decreasing concave down. Let's assume it is decreasing concave up. So it would look something like this. And we ask, could this point be an absolute maximum or minimum? Well, clearly it can't be an absolute minimum. If you go to the right of this point, see here, clearly f attains an even smaller value than at x0. And if you go and you ask, could this point be an absolute maximum? Go to the left, and clearly the function attains an even bigger value than it did at x0. So you see it's clear from our two pictures that if the derivative is positive at this point can't be a max or a min. If the derivative is negative at this point, the point can't be a max or a min. So the only way to have a max or a min is to not be in one of these cases. Well, think of it. What's the opposite of the derivative being positive or negative? If you think of it, draw a line. This is 0. Look at f prime of x. And we're saying, for which values of the derivative can we expect a minimum or maximum? Well, positive values of the derivative will give you an increasing function, therefore no max, no min, so we can't accept any positive values of the derivative. A negative derivative will give you neither a max or a min, so we have to reject negative values as well. So the only possible value, if the derivative exists, that may give a max or a min is when the derivative is 0. But the derivative could also be undefined. That's also an option. And you see this is the only way to attain inside the interval, if we exclude the left and the right hand point, a maximum or minimum value. Because it is impossible if the curve is increasing, positive derivative, or if the curve is decreasing, negative derivative. So the only way to attain a maximum or a minimum value inside of the interval is if the derivative is neither positive nor negative, therefore if it is 0 or undefined. Therefore if the point x is a critical point. And this was our conclusion in our theorem. And again, I want to go over it one last time because this is so important. If you have a continuous function on a closed and bounded interval ab, by the extreme value theorem, the function will attain a maximum and a minimum value inside of the interval. The question is, where should we look for an absolute max and an absolute min? And the answer is surprisingly simple. The function can only attain its maximum and minimum value at either an endpoint of the interval or at a critical point, therefore a point where the derivative is 0 or undefined inside of the interval. And with this now we're ready to look at problems of optimization. And this will be the topic of our next videos.